So today we're going to learn how to do some calculations using time dilation and length contraction equations. So just a quick review. The proper time, delta t0, is the time that's measured in the frame in which the two events occur in the same location. So often when you're doing these problems, the math isn't that difficult. It's just thinking about which is the proper time and which is the proper length. So remember, think about in which frame do the two events occur at the same place, and that'll help you figure out which is delta t0. That factor gamma is 1 over the square root of 1 minus v squared over c squared, and it's always a number greater than 1. So the time measured in the frame that's not the proper frame is always longer than the time in the proper frame. Length contraction. The proper length is the length measured in the frame where the object is at rest, and the length gets smaller by a factor of gamma. So L is equal to L0 over gamma. So let's do some calculations and see how this works. All right, so we have a spaceship traveling at a speed of 0.9 times the speed of light, so 0.90 c, relative to the Earth, and it's traveling to Saturn. The distance from Earth to Saturn measured from Earth is 1.43 times 10 to the 12 meters. So the question is, how far is that trip according to the astronaut? So the question is, which one is the proper length? Well, the astronaut, if I draw a picture, here's the Earth, here's Saturn. The astronaut is traveling as he measures this distance. So he's moving past these things, so he's not measuring the proper length. The proper length is the length measured by someone on Earth to whom Saturn is, well, at least relatively stationary. So the proper length, L0, is the 1.43 times 10 to the 12 meters. And so we are asked to calculate what is L. And L is L0, which we know, divided by gamma. So we need to calculate gamma. So the first thing you should always do when you're doing these kind of calculations, these kind of problems, is to calculate gamma. So gamma is 1 over the square root of 1 minus v squared over c squared. So 1 minus v is 0.9 c. And I need to square that. So v over c squared. And you can see that when I express my velocity in terms of c, the c in the numerator and the c in the denominator are going to cancel out. So I'm going to be left with my gamma is 1 over the square root of 1 minus just 0.9 squared. And so I get gamma is 2.294. Okay, so now I can calculate my L. L is equal to L0 over gamma. L0 is 1.43 times 10 to the 12 meters. My gamma is 2.294. And so I get my new length is going to be shorter, of course. It's going to be 6.23 times 10 to the 11 meters. Okay, so let's now think about time. So if the person on Earth measures the trip to take 5,293 seconds, how long does it take according to the astronaut? And so let's remind ourselves that our gamma was 2.294. And so now we've got to think about who measures the proper time. Right? So when the person is sitting on Earth, what they see is they turn on their stopwatch when the astronaut goes past them, and then they see the astronaut go past Saturn and they stop their stopwatch. So that time, they see the event occur at two different places, one at the Earth and one at Saturn. So that time is delta t, person measuring from Earth. So delta t is 5293 seconds. So we want to figure out what's the time measured by the astronaut. That's got to be delta t0. So does the astronaut see the two things happening at the same location? Yes, he does. So he's just looking out the window of his spaceship and he sees the Earth go by him and he sees Saturn go by him. So according to him, the planets are moving by him. He's just sitting still, and he sees the things go by his window. So he's seeing the two things happen at the same place, just at his window. And so he's measuring the proper time. So we want to figure out the proper time. So if I rearrange the equation at the top, I've got delta t and I've got gamma. So delta t0 is delta t over gamma. Delta t is 5293. Gamma is 2.294. And so I get a time of 2,307, or about 2,300 seconds. So the astronaut measures a much shorter time than the observer on Earth does. So the math is not difficult. It's mostly just thinking about who's measuring the proper time, who's measuring the proper length. Okay, how about a problem where the math is a little bit more difficult? So we want to know, at what speed does a moving clock tick at half the rate of a stationary clock? So what that means is that delta t excuse me, delta t, the stationary clock, measures twice the time as the moving clock. So if I compare this equation and this equation, we can see that then the gamma is equal to 2. Okay, so gamma is equal to 2, and I want to find out what is my v. So now I'm going to say 2 is equal to 1 over the square root of 1 minus v squared over c squared, and I've got to rearrange that equation to give me v. So the first thing I want to do is I want to get things out of the denominator. I also want to get things out of the square root. So first let me multiply both sides by that square root. Okay, so I've got 2 times the square root of 1 minus v squared over c squared is equal to 1. Okay, now I want to get the square root by itself before I unsquare it, so I'm going to divide both sides by 2. So square root of 1 minus v squared over c squared equals 1/2. Okay, so now how do I get rid of a square root? I square both sides. I'm going to square both sides. So I've got 1 minus v squared over c squared is equal to 1/2 squared is 1/4. Okay, so I'm getting there. So now I want to get the v squared over c squared on one side by itself. So what I'm going to do is I'm going to bring the 1/4 subtracted over onto the left-hand side, and I'm going to add the v squared over c squared to the right-hand side. So I move over to the other side of my screen. So I've got 1 minus 1/4 is equal to v squared over c squared. So 1 minus 1/4 is 3/4 is equal to v squared over c squared. We're almost there, so let's get that c squared over to the other side. So v squared is 3/4 of c squared. And now to get v, I take the square root. So it's going to be square root of 3/4 times c squared. Square root of c squared is just c. The square root of 3/4 is numerically 0.866. So it's traveling at a speed of 0.866 c. So make sure you're able to do this math. You're definitely going to see questions like this on the homework. All right, let's do one with length contraction. If we have a spaceship that's 130 meters long by 50 meters wide when it's measured at rest. So if we draw it, let's just make it a rectangle. It's 130 meters long by 50 meters wide. And it's going by you in the direction of the length at a speed of 0.740 c. So what length and what width do we measure? Well, remember, when the thing moves by, it contracts in the direction that it's moving, but the direction that's any directions perpendicular to that are not changed. So what we're going to see is we're going to see something with a new length, but the width is still going to be 50 meters. Okay, so the 50 meter width is unchanged. So what's the new length? Well, remember, when it's measured at rest, that's L0. So we know L0 is 130. We need to find L. And in order to do that, we have to figure out our gamma. So remember, when we have our speed expressed as 0.74 c in terms of c, then gamma is just 1 over the square root of 1 minus 0.74 squared, because the c in the v and the c in the denominator of the gamma equation cancel out. So my gamma is equal to 1.49. So my new length is the old length, the proper length, divided by gamma. So 130 divided by 1.49, and I get 87.4 meters. Okay, so that spaceship now looks a lot shorter, but it's the same width. So I want you to sit down and do 2 questions here, one with time and one with length. So the first one, you're in a motorhome that's traveling at 2/3 the speed of light, and it takes you 1 hour to bake a cake in your oven. So we want to know, how long is the baking time as measured by someone who's standing beside the road and watching you drive by. So again, think about in which frame is the cake put into the oven and taken out of the oven at the same location, and that'll help you figure out which is the proper time. So the second question, you have a 1 foot long, which is about 30.5 centimeter ruler, and we want to know how fast must it be moving if its apparent length is only 20 centimeters. Right, so those 2 lengths are L and L0. You can figure out which one is L because you know which one is shorter. Okay, so you know L and L0, and you have to do the algebra like I did on the last slide to figure out how fast is it traveling. So you need to rearrange it to get the V.